Good afternoon. Thank you very much for inviting me to present at the IEEE conference today. It's a real honor, and I appreciate the opportunity. Let me tell you a little bit about our company. We are Kavi Global. We are based in Chicago suburb of Barrington. We have been in business for the last 9 years, and we focus primarily on the data analytics in all aspects of data, from the data gathering, data warehousing, data quality, data management as a whole, and all the way into advanced analytics, business intelligence, and reporting, and so forth. Here we have some of the recognitions and awards that we have received over the last few years. One of the reasons I wanted to mention is the Gartner recognition. We have been featured on one of their market guides on advanced analytics and machine learning recently. From the industry perspective, we work across multiple industries. Industrial and manufacturing, transportation, state and education, financial, healthcare, pharma, and digital marketing. Today we have 4 customer-facing practice areas. First one is the strategy and design services. We help our clients figure out the strategy, how to accelerate and scale their analytics. So we work with them on their current state analysis, work with their leadership, identify the digital transformation needs, and we help them develop roadmaps and how to go about it. The implementation is the project implementation team, research and development team. Research and development is big for us. We have been working in the research and development side since the inception of the company. So that's a key differentiator for us. One of the things we are going to talk about today is how fundamental research is done in the R&D department to make the role of the data scientist more productive and efficient in the future. That's the theme of the discussion today. Operation support is the other area. We do a lot of the cloud and on-premise management of applications and infrastructure for our clients. So the agenda is, I want to start with big data in business. We want to pick one industry and talk a little bit about how analytics is impacting in that industry, and then generalize it to multiple industries and talk about high level what are the challenges the organizations face as they get on to data analytics. And then the R&D approach we have taken and the innovation to address these challenges. What's our approach? And then I am going to invite one of our data scientists from the R&D department who will demonstrate some of the tools and a day in life of the data scientist in 2020. Srini will come on stage for that portion of the presentation. So let me start with big data in business, particularly in healthcare. There are a lot of challenges and developments happening in the healthcare industry. The primary challenge there is the changes driven by the Medicare and Medicaid, CMS, primarily due to the new direction to shift to value-based models from what we call today pay for service to pay for outcomes and quality, and all the way to pay for the performance. It's, as you know, it's a complex ecosystem with many players, from the providers to payers to many other service providers in between. There's also increased competition in this space. There's a lot of deregulation, so to speak. For example, pharmacists can now perform some of their the prescription and other services that a normal medical doctor would provide. And as you know, other clinics and others are popping up, competing with the hospitals and other providers. With all that, and some of the other development, technology development in various ways of getting the information from the health information from the humans all the way to wearables, there's an explosion of data. And if you look at the entire ecosystem, there are thousands of data analytical use cases. The bottom line is to stay in business and compete and grow and do well. A lot of these organizations need a robust data analytics capability. Now, that is the case with all of the different industries we work with. The primary need is stemming from the increased competition, complexity in the regulatory environment drives the need for digital transformation. So all of them are right now looking to see how they can accelerate and efficiently scale data analytics. So let's talk about the challenges of today. The challenge number one is the technologies. I just did a Google search on big data technologies, and this is what comes up. And what's the challenge here? The technology stack is becoming increasingly fragmented and complex. So new technologies are becoming available at an increased pace. This is good for the most part, but it also is bad from other aspects. Think about the solutions obsolescence risk. Whatever you built a couple of years ago, now you have new technology options. So the solutions are becoming obsolete. And also the skills. The people have to continuously learn new technologies, be able to work, program, code in these new technologies. So the first question is, how can we mitigate these risks? The second challenge is there's a perceived shortage of data scientists. And I did another Google search on this, and depending on who you talk to, it can be anywhere from 15,000 to about 1.5 million in the next few years. The question here is, before we get into discussing the shortage, let's talk a little bit about the data analytics organizations and processes. This is a conceptual diagram from one of the large organizations, how the analytics competency is organized. If you look at it, there is a collaboration or working together from the business side, the IT side, and the leadership side, and there are a lot of different competencies like the data science, visualization, data, and BI, and all of the solutions require a lot of working together. So for large organizations, there are multiple teams, generally distributed across the globe in even various different countries or geographic regions. And there's a very high level of inefficiency because this work process or the supply chain of analytics is labor intensive. So that drives the real answer. Is there really a shortage, or there's a process inefficiency, or both? The process here, what I call the craft mode. Craft mode is way back when, before the Industrial Revolution, how we used to make things from violins to antique tables and other. The challenge there is that it's highly labor intensive, low process efficiency, and high cost. The advancement from the craft mode to scale and accelerate analytics is what we call the lean mode. So the question here is how we graduate from the craft mode to the lean mode. So imagine a platform that will enable to increase the productivity of the labor in the analytics supply chain, achieve flexibility in many different ways that you can work across the various disciplines I mentioned earlier, from the data acquisition to data quality management to data integration, all the way to the advanced analytics and reporting and other. And how do we mitigate this risk, the solution obsolescence and the people skill obsolescence, and how do we drive the automation into this process through this platform? So the platform capabilities, in order to graduate from the craft mode to lean mode, we have to make it more efficient. So one of the ways you can make it efficient is by not having to code. Humans do a lot of coding activities, but nowadays, given the capabilities of machines, we can automate that. A human can define logically what they're trying to accomplish in the data management and analytics and business rules and advanced analytics, and most of the code writing can be automated, giving a seamless interface to the human with no code. And it can be integrated. Today the stack, technology stack, is very, very fragmented. If you look at from the data ingestion to data management to advanced analytics, you have at least a half a dozen tools, half a dozen different interfaces. So if you have a seamless interface integrating all those capabilities, if it is comprehensive and integrated, that drives a lot of efficiency as well. You can reduce a lot of the overheads, such as the communications overhead. These multiple teams have to be in a lot of different calls discussing the process and what you did to a particular piece of data. For example, as you acquired it from the source systems all the way to all the transformations and logic you have to implement through to the analytics modeling process. So you can cut down on the documentation, communication, and other overheads. And if you can also make it a multi-technology, that means directly the people are not exposed to the technologies. They don't have to code in a specific technology. So to speak, you can change the engine under the hood without impacting the people, if you can think of a multi-technology environment. So that's exactly what we have been able to develop in our research and development. The first, what you see here in orange is what we call the interface or the application that accomplishes all of the features I discussed previously. So it's simple and integrated across the collection to the preparation and the analysis, all the way to the decision-making processes. It's automated and the technology is abstracted. In this case, we're talking about the both commercial and open source technologies. So with that, I will ask Srini to come and take the next part of the presentation, which is the actual demo of the platform, and discuss how his role is changing, what a data scientist would do today versus how they are going to work in 2020. So with that, Srini, please come to the stage and proceed with the demo portion of the presentation.
Thank you, Vijitha. Today I'm going to just demonstrate the points that were made by Vijitha on the future of a data scientist, using 6 points, and I will also be showing you 2 use cases on how a data scientist can easily create and solve business problems that comes in his way. So let me start. I would start with 6 points that are necessary to increase the productivity of life of a data scientist. First one, comprehensive capability ranging from data ingestion to data management to data analytics to visualization. So right now, the issue that a data scientist faces is he needs a lot of tools to do each of these individual capabilities. There's no one single tool that can enable a data scientist across this entire data value chain. So that is point number one. The second point that would increase the productivity of a data scientist is the ability to drag and drop, or the ability to use a menu-driven interface instead of coding. So with the advent of new and newer technologies, it kind of compels a data scientist to learn new languages and to code in them. So this reduces the productivity of a data scientist. So if there were a capability to drag and drop without the necessity of coding, that would definitely enhance the life. The third point is ability to ingest data sources from various data sources. So earlier, what I as a data scientist used to do was probably look into data from file systems and traditional DBs, databases. But with the advent of big data, what is happening is there has been lots and lots of data sources. For example, you see that we can get data from streaming data sources, from web blogs, from Twitter feeds, from Facebook feeds, stock market feeds. There are lots of data sources that have come up, and there needs to be the ability to connect to all these data sources and use these data sources for analytics. That is point number 3. Point number 4 is the ability to use multiple compute engines. One would not want to be restricted to one particular technology if you want to do the analytics in a most efficient manner. I would want to switch over from one technology to ingest data to another technology to do the actual analytics per se. So the ability to switch or use multiple technologies, execution technologies at the same time, is another feature that is required. The next one is what I call the technology abstraction. We don't want the transformation logic or the analytics logic to be buried within one code or within one technology. So if you write a particular code to do a regression analysis, for example, you write in particular one particular technology, say R or Python or whatever it may be. We want to abstract the actual regression algorithm away from that particular technology. I will show you how. And the next thing is, this is pretty obvious. I would want exhaustive list of capabilities so that I can do any operation that I may want to perform for transforming the data, for enriching the data, or to do analytics. So a comprehensive and exhaustive list of capabilities is something that a data scientist would want to increase his productivity. And the last thing is easy migration from one technology to another. So what we have seen in industry is that we have been creating various logic, both transformation and analytical, in particular technology, and with new and new technologies coming and taking over, we end up a lot of time actually migrating from one technology to another. So what we would ideally want in the future is to migrate from one technology to another by a single click of the button. So these are the 7 points that would make the life of a data scientist easier in future, and this is the way that analytics and data transformation is certainly moving towards. I will show you an example of each of these points that I have made with specific examples. Let me log into a tool called that I am using. So I'm going to log in here. Okay, so I'm using a tool here. Let me go to the first point that I made: comprehensive capability from data ingestion to data preparation to data enrichment to analytics and visualization. All these capabilities I would want in a single user interface without the need to switch over from one tool to another. So that's what you are seeing here. So in this particular tool, we have data management capabilities. I can do data transformation, perform data quality checks, profile data to see outliers, for example, and then I can define business rules, define workflows, and I can perform data analytical operations like regression and classification, and then view the results using creating visual reports, and then I will be able to view them in a portal. So and then also there is a data glossary to store the definitions as a single source of truth, and then there is the ability to create workflows to schedule various functions one after another. So this is what I meant when I said a data scientist needs a single unified tool that can perform a range of functions across the entire data analytics value chain. Now let me go to one particular module to emphasize my second point, which is menu-driven interface without the necessity to code in a particular language. So this is a data transformation operation that I'm going to do, and let me click on one of the transformation flows that I have already created as a sample. You see in this example, what is happening is the data is getting ingested from 3 different data sources, and they are being read, and the data is merged, and the customer, this is a scenario in which banking analyst is trying to risk stratify the customer into 4 different categories. So all this is happening without the need to code. I just drag and drop the required data and tasks into the canvas, and I can edit these with a single click of a button, and I will be able to edit any of these parameters that are needed to make my transformational flow. So this is how what I mean as a menu-driven interface. I just click on any of these, and I will be able to add or edit or remove any of these functions that I want to perform. So this was point number 2. So I have a drag and drop interface or a menu-driven interface without the need to code to do the operation that I want to perform here. And let me show you how I can have the ability to ingest from different databases or data sources. That's what I would demonstrate to you right now. For example, if you see here, I would want to add one particular data from, let's say, a data source that is not already available to me. So the first thing that I would choose here is the type of data that I want to include in this particular transformation. So the data can be a file, and within a file it can be different types of files, say delimited or fixed length, and it can be a table from a traditional DB, or it can be even XML and JSON formats, which is how most of the newer and newer streaming data is formatted in. And coming to the data sources, you see that I have the ability to get data from these different data sources. You would observe that you see that there is a traditional JDBC, the traditional databases, and also the newer NoSQL databases such as MongoDB and Cassandra, and also you have file systems like FTP and streaming data from queue systems like Kafka. So this gives the ability for a data analyst to get data from different data sources and not constrained from where the data resides. This is the third point that would make data scientists more productive. And let me move to the fourth point, which is the technology abstraction. So technology abstraction works in 2 levels here. So the first thing is the actual transformational flow, which is the risk stratification of customers in this particular example is not actually coded in a particular language, but here it is just the transformation flow or the logic of transforming itself is stored separately away from the actual underlying technology. So that is the first level of abstraction. And once the transformation logic is to be executed in say technology 1, it gets converted to the code of that particular technology, for example Spark. And then if I want the same risk stratification to be executed in another technology, for example in database Greenplum, then the logic gets transferred to the second technology. This means that there is no need to actually integrate or tightly integrate the transformation or analytic logic with the particular technology. If we keep both of them separate, we can convert that the transformation or analytics to any technology that we want, which I will show you in a minute. And this was the first technology abstraction, and the second level of abstraction is what we call as abstracting the business rules and the data quality rules away from this particular transformation flow. For example, we have certain business rules that we are using in this particular flow, but the rules themselves are not defined here. The rules themselves are actually defined or being created in another studio, which is away from the actual place where this logic gets executed. I will show you briefly how the rule gets created and how the rule gets executed. For example, we are talking about the same rule in which I want to risk stratify my customer. So let me open that particular project here. Yeah, and let me quickly show you how the rule is created or defined. So this is where I come to define the rule, and what we mean by a business rule is it's a set of or a series of conditions and actions. So I specify a condition, and if a condition is met, I specify an action for it, and I will also specify an action if the condition is not met. So these rhombus indicate the conditions, and these rectangles denote the actions. For example, if you see here, there is a high risk condition. Let's see how I have defined a person or a customer as high risk. So what I have defined is an annual income less than or equal to certain amount, and months since last delinquency should be less than the last 12 months. So that's how I have defined the high risk customer, and defining here means that using those definitions, I can actually apply them on a data in the transformation studio in this particular transformation flow. So I have defined a condition or criteria for high risk customer, and then I also define the actions to be done. The action here is tag a particular customer as a high risk customer. So all these definitions are done on logical objects. Till now we have not physicalized the data on which the rules have been defined. So I will come back here and show you how the rules are actually physicalized or invoked in a particular transformation flow. So just to repeat, the logical rules have been defined here, and the actual physicalization of the rules happen in a particular transformation flow. So what I need to do while actually I get the data and apply those rules is to just map those logical rules and the logical elements to physical column names. So once I map these, whatever logical rules I have defined in the other part will get invoked or will get applied to that physical data in this particular job. So this is definitely an advantage to the analyst in the sense that if I have to write the same rules in say 5 or 10 different jobs, I don't need to write them in each and every transformation flow, but I just need to define them in one particular place in the rules studio as I showed you, and then I just need to invoke them in each of these transformation flows, and even changing or editing a particular rule becomes easier so that it need not be done in each and every job. That's what I meant by technology abstraction, and even the rules and data quality definitions abstraction away from the actual analytical flows. Yeah, Let me actually move to one of the important points that a data analyst requires definitely in the future, that is the ability to use multiple compute engines. As I said, technology is constantly evolving and newer technologies are coming into play, and what our data analyst needs is the ability to use the same transformation flow or analytical objective into multiple technologies. Let me give you an example. I'm going to show you two use cases in detail, and those use cases, for example, one is predicting the readmission of a customer. So the prediction of readmission, that business objective remains constant. However, the technology changes, I still need to predict the readmission probability of a particular patient in a medical setup. So that particular objective, I need to be able to, the regression or the prediction, I need to be able to do it in newer and newer technologies. So that ability, if it were available to me without the complex process of migrating from one technology to another, that would definitely help in my productivity. So I will show you how that can be done here. So if I want to create a new transformation flow, I click on this particular button here, and I will say create a new job, and when I want to create a new job, I will be asked to choose from many options available in this execution technologies. So if you see here, I have 5 different technologies to do a particular analytics objective. So I have say Spark with Scala or Greenplum or in database Redshift, and I would choose anything that best suits my transformation requirement or analytical requirements. So this, on a click of a button, if I am able to do this, then nothing like that. That is really enabling my productivity here. So that was my fourth point, in the sense ability to use multiple compute engines as and when I need, depending on my exact requirements. Yeah. The next thing that I would probably want to highlight is the comprehensive list of data management capabilities, and also the comprehensive list of analytical capabilities. If you see here, first let me take the example of the transformational requirements that a particular data analyst needs on a day-to-day basis. First, I may need to access the data from different data sources. So what I find here is the entire list of accessing requirements, and then the next thing that I want once I access the data is to transform the data. So here I have a very comprehensive list of the different features that are required to transform the data and enrich the data, and once I have transformed the data, then I may need to invoke or apply data quality rules or business rules here, and also a preliminary set of data analytics, like performing summary statistics on the data. So the last point, or the most important point that I want to highlight, is the easy migration capability from one technology to another. As I said earlier, what we often find is we spend a lot of time developing one analytics algorithm in one particular technology, and when we want to adopt a newer technology, say I want to adopt a big data Spark, what we end up doing is to recreate the entire analytical or transformation logic in the newer technology. This is not value adding, in the sense that I have recreating what I have already done again and again, since I want to move to newer technologies. So what would definitely help, or the way the future is moving, is to migrate from one technology to another by a single click of a button. Let me show you how. So I just need to click on a thing called, say, migrate job, and once I click here, and I am asked to specify the newer technology, underlying technology that I want to migrate. So I can select, let's assume that I have an underlying job in Greenplum and I want to move it to say Scala, Spark with Scala, and I need to choose the version. I will choose the newest version in that, and I will add an instance. The instance here is the server, and I just need to give a new job name. So I will give you some name here, new job, and I need to just specify the folder in which the new job will be stored. And once I click on migrate, that's it, it's migrated. The same risk stratification transformation that I had created in Greenplum earlier and was executing in a Greenplum database will now execute in Spark. If I had to do that manually, it would be probably weeks or more than a week's effort to just understand the technology, or understand the transformation flow in the older technology, and code each and every step here. This job probably contains some 15 or 20 steps. Each of those steps have to be recreated in the newer technology. That would definitely create lot of time and effort, and will also be prone to errors. So, but what I just showed you, with a click of a single button, when I am able to migrate to a newer technology, then it reduces the time, reduces the effort, and also reduces the error probabilities that may arise when I am coding in the same logic. So, I just demonstrated you the 7 requirements or functionalities which will help to make the life of data scientist easier, and how these capabilities are definitely the way how this data science world is moving towards. Now I would want to pause here briefly and show you some of the analytical capabilities that as a data scientist I am required to perform on a day-to-day basis. The first case study, both of these case studies are in a medical or a healthcare setup. So the first case study is to predict the readmission likelihood of diabetic patients within the next 30 days. Before I go deeply, let me briefly give you a background of it. As you would have all known, the insurance market has changed a lot and is undergoing change recently. So in the past, what happened, the Center for Medicare and Medicaid Services, which is the nodal agency for implementing healthcare payments, so the CMS used to pay for providers or doctors based on the service that they have given. So it was a pay for service model. And it didn't take into account the outcomes or how good the treatment or care given. But now it has changed from pay for service to pay for outcomes. In the sense, the providers and the doctors, providers or doctors will be paid based on the outcomes of the actual care given. What do you mean by outcome? In the sense, how good was the treatment to a particular patient? Is he getting better based on the treatment given? Is he improving based on the care given? These are all the metrics that will be taken into account for payment towards providers. And one of the metrics to measure the outcome is the readmission likelihood of a patient. So if a patient is undergoing some treatment for a disease, let's say diabetes in this particular example, and he gets some care and he gets medicines for that, we don't want the patient to go back to a care center to undergo treatment for the same treatment within 30 days. That means that the prior treatment was not as effective as we would like to be. So what happens is we want to predict the readmission likelihood of diabetes patients. Hospitals and doctors are very much motivated to see this metric, so that even before undergoing the treatment, if we know that this patient has the likelihood to get readmitted after some time, we would be able to provide more extra care, and we will be able to modify our diagnosis and treatment methodology in order to prevent that in future. And even this will help in terms of post-treatment care or post-treatment guidance to the patient, so that he doesn't get the same medical emergency within the next 30 days. So we have a motivation here to predict the likelihood of a diabetes patient within the next 30 days. And as a data analyst, I have been given some data. So let's see what those data are. The data are the member here means patient, the patient's demographic information, like what is his age, what is his prior medical condition, and so on and so forth. And then we also have the drug history and the drug interaction information. We in this particular analytics, we are taking the details of probably more than 40 drugs that can be prescribed to a diabetes patient. So we will have the entire history of what drugs were prescribed, and how and if there is more than one drug, is there any interaction between those drugs that were prescribed. So there is this drug history information. And then obviously I will also be given the historical treatment records. So what treatment did he undergo in the past, how frequent was this treatment taken. So all this information are available. And the methodology is, I have already prepared the data. Since the analytics requires the data to be prepared and enriched, I first prepared the data, and then I used different modeling methods. You see the different modeling methods. I used logistic regression, classification, gradient boosted tree classification, and I also used naive Bayes. So I've used different set of modeling techniques, and used the best modeling technique which to me gave the best results. So this is how I went on and created this particular methodology. Let me show you actually the particular transformation flow which predicted the readmission probability. Yeah, let me open this. And this analytics flow is what I did to predict the readmission probability of a diabetes patient. So I ingested the data, and then I did some feature engineering steps, which mean that I need to transform the data from one format to another, so that the downstream analytics can get the data in the format that they want. Let me just show you the different feature engineering and feature transformation capabilities that I have. So this is the feature transformation. There is this entire list of exhaustive feature transformation capabilities, which means that I can transform the data from one format to another. And then there is feature extraction, feature selection, and then comes the actual modeling. The next four are the modeling techniques. So I can do clustering if I want. So I can have k-means, bisecting k-means, and going to the advanced clustering techniques such as Gaussian mixture. And then there is this regression and classification. So within regression, I can perform the simple variants like linear regression to advanced ensemble models like random forest, gradient boosted survival, etc. And if my objective function is to classify, I have different tools available. I have the basic logistic regression to advanced models like multi-layer perceptron, which is the neural networks. And then also I have ensemble models like random forest and gradient boosted tree. So I have a very exhaustive set of tools available, and based on that I can perform, I can transform the data and then apply the data to the transfer to the analytics models, and then perform the analytics. So if you see here, I am performing logistic regression, random forest, gradient boosted, multi-layer perceptron, and decision tree. So all I need to do is execute this job and wait for the data to be analyzed and the results to be given to me. So in an earlier setting, what would have happened is I would probably have to code all these analytical steps in a particular technology, and that would have taken me probably a week or more. But now this creation of this particular analytics flow took me less than a day. And if you see, even the execution here takes very little time, and the actual processing of the data into various technologies it's all a matter of minutes before the results are shown. The analytics flow has run, and now we will be able to see the results. Okay. So most of the times the analyst spends a lot of time in viewing the results and trying to understand them. So, but viewing the results is also very easier with this tool. So what I need to do is since this is a classification problem, I need to predict whether a patient will be readmitted or not. I just need to go here and see the classification summary to see how good my model is. So I just need to drag and drop the required metric that I want to use, and then I can see the results. For example, I see that the prediction count and actual count are almost the same here, and that says that my model is really good. I can drag and drop the statistics summary, which will say how good the model is. So let me drag and drop the statistics summary, and I see that the area under ROC, which is one of the metrics to see how good my model is pretty good. But this may not be as good as the other models. So let me also compare the other models and see which model is the best. For example, this random forest and gradient booster, these two nodes use an ensemble of models themselves, so that it is not the results are not from one particular tree but from different trees. So if I drag and drop here, I can see that the results are once again the results are very, very good. The misclassification is very low, meaning the blue indicates the correct classification and the black indicates the incorrect classification. So this is almost good. Like similar to this, I can go to each of these models and find out how good or bad these results are and select the best model that predicts the readmission probability. The other thing that I would highlight here is the model tuning. So if I find that a particular model is not giving good results, I may need to fine tune the model. I may need to provide different parameters to a particular algorithm, so that it will use the more than one parameter and get the best results based on whichever parameter it chooses. For example, here what I have done is there is a regularization parameter which is used to reduce the false positive rates. So this regularization, I have provided various parameter values. The convergence tolerance is another parameter. I have provided some parameters. So what the model tuning will do is it will choose the best value out of these parameter values that I have provided and choose the best to give the most accurate result. In this case, in this way, the model tuning the model that I have already created becomes very much easier, which otherwise would have taken a similar time or even a longer time than actually developing the model in the first place. So model tuning is another place where there is a possibility of increasing the efficiency of a particular data analyst, and this is tools like these definitely help make the life of a data scientist more productive. So this was the first use case that I was talking about, and let me go to the next use case, which is suspicious claims detection. So again, in the healthcare scenario, there are lots of insurance claims submitted to insurance companies based on prescription claims. So if I go to a doctor, he prescribes some medicines. So I, as a patient, go to the pharmacy, get those medicines for me, and I submit the claim, or the pharmacy submit the claim to the insurance companies. So it's more than the total number of claims, or prescription claims as we call them, for getting medicines was in the range of more than $500 billion in the US alone. So this is a huge number, and what the authorities and the insurance companies have found was many of these, a significant number of these, were spurious. Even if we assume that 1% or 2% of these claims were spurious, it goes to billions of dollars. So we would want to identify suspicious claims on the prescription drugs. That is the objective or motivation for this analytics here. So what is the data that I get is, I want to get the patient demographics, meaning details about the patient, details about the doctor who prescribed the medicines, the actual prescription itself, meaning how many say tablets were prescribed, how many course of medicines were prescribed, what was the length of the prescription. So there is a lot of details that is regarding the prescription itself. And then the pharmacy, I as a pharmacy submit a claim to the insurance company. So what is the frequency of claims that I have submitted? Is there a pattern of giving some drugs over other drugs? So there is this pharmacy demographics that are available for this analytics, and the actual drug characteristics, and the payer information. In this particular information, it is restricted to one particular insurance company, or PBM as we call it, pharmacy benefit manager. So the methodology is, again, I prepared the data using the Plexa tool, and then in this case we don't know if a particular claim that has been submitted is suspicious or not. So we don't have that indicator already available with us, as opposed to the last case study in which we had some data which said that this person was admitted or not based on historical information. Here we don't have that information. So normally what we do is we use one type of analysis called unsupervised learning, in which we don't require the data, the objective data, to be already present. But in this case, we took a slightly different route. What we did was, there is this unsupervised random forest classification. So we used a supervised technique in which random forest is one of them, and we used this to mimic the unsupervised learning by creating synthetic noise data. So we have this information of claims that are submitted, and we are to find out if some of the claims are suspicious. So we created some new synthetic data by randomly populating values for each of these variables. For example, if we know that, let's say, if we know that there is a age variable available for this, and then there is a drug name available for this. So, and if we know that for this particular age, this particular drug is not normally provided, we actually created some new synthetic rows or observations which randomly selects some age and some drug information. If it is random enough, we can assume that these kind of prescriptions will not be made for this particular age, and these are more likely to be suspicious. So the synthetic data that we have created are more likely to be not found in a normal scenario, so they are suspicious, and our objective here is to find out within the normal data that we have been provided, what are those observations that more resemble more likely to the synthetic data that we have done. That is how we have gone forward in this particular analytics. So let me again go back to the tool and show you how we went about performing this analysis. So let me open this particular job here, and let me open this analytics flow in which I am trying to find out the suspicious claims. Again, what I have done is I have ingested the data. So this is the actual data or the original data, and this is the noise data or the synthetic data that we have created. We ingest both of these information and merge them, and then actually apply the model building within using random forest classifier, and then write the results to a particular location in our system. So let me once again execute the job. Yeah. While this job is getting executed, one point I would highlight is this pipeline functionality that I'm using here. So this is again one of the productivity boosting tools or functionalities that I have at my disposal. So what this pipeline does is, in a normal scenario, a data scientist is required to prep the data and enrich the data to actually create the model, which is the training data as we call it. And once the model is created, he needs to the actual data flows in, and the model gets applied on the data to see the results, which we call as the scoring data. So the data needs to be prepped each and every time for training data as well as the scoring data. So this is a redundancy that we face in model development process. So this pipeline kind of removes that necessity. Within the pipeline, we can have any number of tasks in which both the training data and the scoring data can be applied, and automatically the same series of steps, say the data transformation steps, will be applied to both the training data and the scoring data, such that there is no repetition of the model development process for each of these individual data elements. So this model tuning and pipeline are some of the other productivity tools that are available for data analysts to create perform analytics very productively and in a fast manner. So these steps are run, and right now it is in the last step to write the data into a file system that I am pointing to. So that's where it is. Yeah. The job has now finished executing, and let's see the results. So this random forest classifier is the modeling method that I had chosen for this particular problem, and let me expand this, and I would want to see the results of it. So let me drag and drop one particular, the misclassification chart that I'm interested in, and it gives me how good or bad the results are. Okay, let me also see the classification summary here. Yeah. So if you see here, all the ones or the synthetic data have been predicted as 1, and some of the original data, say this count of original data, have also been predicted as probably suspicious claims. So these are the claims that mimic the synthetic data that we have created. So as a downstream process, these particular claims will be taken up for further investigation and to find out if these are suspicious enough. So this is one example of using a model to solve an actual real life problem. So to recap, what we have done is we had used random forest classifier to predict or to identify those suspicious claims made by pharmacies, and which will then be further investigated on. So this concludes the 2 use cases that I have. To recap what we did today, we saw the various functionalities, or 7 functionalities to be exact, that will make the life of a data scientist more productive, and that is certainly how the future of data science is moving towards. Thank you very much.